After prototyping the crossed-lamellar CFRP using two different procedures, we wanted to know how the microstructures perform when we test them. So we tested the microstructures in 3-point bending in an SEM environment. We paused the tests at regular intervals to capture images. This is how the microstructures look like in the SEM, with the 3 macroscopic layers highlighted. Next, you will see images at an early stage of the test and at the end of the test. At an early stage of the test, both specimens have tunnel cracks in the inner layer, deflected cracks in the middle layer, and some delamination at the macroscopic interface. At the end of the test, the co-cured specimen has failed completely, while the bonded specimen is still carrying load. In fact, we reached the maximum displacement of the tester before the final failure of the bonded specimen. And if we look at the load displacement curves, all the load drops are caused by specimen relaxation while we pause the test to take SEM images. We can see that both microstructures dissipate energy under stable conditions, even more so the bonded specimen that dissipates energy under increasing or constant load up to large displacements. After the tests, we wanted to know what kind of damage there is in the specimens, so we broke them in half to look at the fracture surfaces. We saw that the cracks really nicely follow the ± 45-degree orientation in the middle layer. We also observed large triangular debonded areas, and within these debonded areas, we saw regular arrays of splits along the fiber direction. These are all signs of extensive diffuse damage. However, if we go back to these images, we can see that while we got all this diffuse damage in the middle layer, the damage in the inner layer is very localized with only a few tunnel cracks and delamination at the macroscopic interface. So we started thinking, is there a way of improving the damage diffusion of this microstructure?